good morning, and thank you all for the opportunity to be here and to share some of my previous and ongoing research, as well as talk about a topic that's really important and interesting to me, at least, and that's fire suppression and mesophication of pine and oak forest, and what that means for burning our forests today. And I'll go into what mesophication is and how it fits into this whole question. And so for those of you who don't know me, my name is Heather Alexander. I'm an assistant professor of forest and fire ecology at Auburn University. I just started about a year ago here at Auburn. Prior to coming here, I was at Mississippi State University and the Department of Forestry for about 5 years. And here at Auburn, I run our forest and fire ecology lab. And so I mentor graduate students and undergraduate students, and I teach our forest fire management course and our forest ecology course. And I'm basically set up to, help train the next generation of forest and fire ecologists. And that's really what gets me excited and what I'm really happy and excited that I'm able to do. And so if anybody wants to contact me after this talk, my email is right there and my phone number. Please feel free to reach out to me with any questions or concerns, and I'll make sure that I get back to you. So our lab is very interested in trying to understand how fire influences the composition and structure, the function and fuel dynamics within forest across a variety of different forest ecosystems, and then how those things feed back to influence fire behavior. And so we address questions related to these feedbacks in a variety of different forest ecosystems, including Southeastern pine and oak forest, upland hardwood forest in the Appalachians, dryland forest in the southwestern US, and then a considerable portion of my research program is focused on wildfires and boreal forests of Alaska and Siberia. So the two questions that my lab is addressing in Southeastern pine and oak forest are, one, what are the characteristics of different trees, their crown characteristics, bark characteristics, leaf litter traits that influence understory fuel bed conditions and growing conditions in a way that act to either promote or suppress fire. So we call these biotic feedbacks because it's really traits that are biological, that are determining whether or not fire can move through a system, and then which species are able to grow in an either fire dependent or non-fire dependent ecosystem. And so that'll be part of what I'm talking about today when we get into this mesophication question. But then from a more applied perspective, we're very interested in trying to understand the ecological role of fire in current day forests. So what is it that fire can do for a forest that can improve habitat, that can alter carbon sequestration, that can influence seed production and the availability of mast, those types of questions. And so thinking specifically about when and where we can restore fire to systems that have had fire removed from them for extended periods of time. So today I want to talk about the legacy of fire suppression in the Eastern US on burning today through impacts on what I'm calling bottom-up controls. And so all of us are interested in restoring fire to the landscape. And if we ask ourselves, what is it that determines whether or not a forest is flammable, we think about things in terms of what we call top-down control. So one of the first things you might think of would be weather. So if we want to burn our forest in, usually we go to NOAA, we look at the weather predictions and we look at things like wind speed and wind direction and relative humidity and air temperature, all of the things that we know drive the behavior of fire on the landscape. So weather and climate too, thinking about where we're sitting on a regional map. Are we next to the coast? Are we in the upland? Are we on top of a mountain, or are we in a bottomland? You know, climate also is very important for determining what kind of conditions we're going to see in our forest stand. So these are what we call top-down controls. And then bottom-up controls are more of the biotic factors that influence fire behavior. And so these are things that we also think about when we're trying to figure out whether or not we want to burn and how a fire is going to behave. But it's stand characteristics. So what, you know, how open is our stand, or how shaded is it? What types of species are growing there? Is it pine or is it water oak? And then we think about fuels. Fuels are biotic as well. So what types of fuels do we have? Is it coarse woody debris? Are they herbaceous live fuels, or is it mostly leaf litter? How moist are those fuels? All of those are what we call bottom-up controls. And bottom-up controls are driven by the vegetation itself. And they're extremely important for determining fire behavior. A stand is not just a stand, right? We all know that there's different traits of both trees and how those trees are structured in our forests that influence the way that fire behaves. So today, I want to get into thinking about what the historical link between forest composition and structure and fire has been, how that link was decoupled after European settlement in this country, the encroachment of tree species since fire suppression policies were put into effect that do not like fire. So we sometimes call these mesophytic species, or fire, and which are often fire sensitive species. So they're species that like to be in environments where fire is not the primary disturbance. And then the consequences of these species that don't like fire encroaching onto the landscape for returning fire. So what has happened is we pulled fire out of the system. We've had encroachment by tree species that don't like fire. And now those species are there and we have to deal with them. And there are many consequences of having those species there for our ability to return fire to the landscape. And this is often termed mesophication. So meso meaning wet or moist. So the systems are getting more and more moist because of the encroachment of these species. And that's making it harder to return fire to the landscape. So this idea of mesophication was that term was first coined by Nowacki Abrams in 2008. They published a paper in Bioscience that was called The Demise of Fire and Mesophication of Forest in the Eastern US. And basically what they're showing is what we call a positive feedback cycle. So this is, you have prior to European settlement in the pre-1900, stands are relatively open. We took fire out. These fire sensitive or species that don't like fire start to come into the forest. The forest gets shadier and shadier. And then those trees, because they shade the understory and also because they have other traits, which we'll get into here in a minute, that suppress fire, acted to create conditions that got continually more moist and more difficult to return fire to the system. And so the idea here is that unless fire, there's going to be some point in all of this, unless we put fire back into systems that historically had fire, it'll be increasingly difficult to burn them because they're going to be occupied by so many of these species that are simply not flammable. So prior to European settlement, forests and fires were interdependent. Forests needed fires to be healthy, and fires depended on forest with a particular structure and composition to create flammable fuels. So this is a really important point, I think, because we often think about fires driving vegetation, but vegetation drives fire. These things interact with each other. And so oftentimes, at least in like the paleo record where we see fire being dominant across the landscape, it's because vegetation the vegetation that was there was highly flammable. And so if there was ignition by lightning or Native Americans, that vegetation burned very easily. So prior to European settlement, if you look at the map on the left, this is in the past, it shows that most of the southeastern and eastern US was dominated by pine, a combination of oak and pine, and then oak hickory as you got up into the southern Appalachians. And then if you look at the map that's on the right, you can see that those forest types were occurring on the landscape where there were low severity, relatively frequent fires. So that's that kind of orange. You can see most of the eastern US was orange. So low severity, frequent fires. And these periodic low intensity fires occurred approximately every 2 to 10 years across the Southeast in both pine and oak forest. So sometimes people think of upland hardwoods as not being fire dependent, but in fact they are. Many oak species depend upon fire for their continued growth and survival. And so this is a map based on the physical chemistry fire frequency model, where they recreated historical fire return intervals across the United States. And you can see that the eastern US is mostly in that kind of orangish range, and that's between 2 and 10 years fire return interval. So relatively frequent fires, and these were low intensity fires, mostly surface fires. And then pre-settlement, we think that most of these forests were open forests. So today, oftentimes when we look at forests, they're relatively closed canopied, so not a lot of light reaching the understory. But if you look at this map on the right here, which shows those zones that I just showed you in that map of the past forest ranges, those oak pine and oak forest are all in shades of gray. So they were open forests. These are forests that look something like the oak forest on the left, or maybe you're more familiar with longleaf pine forest here, but there were relatively low density of trees, a lot of light reaching the understory. The understory was comprised mostly of herbaceous vegetation, and that was the primary fuel source in these systems. And so there's lots of historical accounts, and I always find these kind of fun to read what people were saying hundreds and hundreds of years ago about what this country looked like prior to European settlement. And so this is a quote from Thomas Morton in 1632 that was published in a manuscript by Bromley in 1935. And just to read you part of it, it says, on one subject, all are in accord, and that is the observation that the original forest was, in most places, extremely open and park-like due to the universal factor of fire fostered by the original inhabitants to facilitate travel and hunting. So he's referring to Native Americans who really were the first fire practitioners and fire managers, and they knew how to use fire, and they used it a lot to, make traveling much easier. So you can imagine if you're riding on horseback and it's more open, it's easier to get around, it's easier to hunt. A lot of berries respond positively to fire, mass production probably increased. So they were using fire, and the forests were likely open. So going back to these original maps that I showed you, and now looking at how things look today, the current composition of the eastern US is quite different. You don't see those distinct zones of different forest type like you did prior to European settlement. And what you see is sort of this intermixing of types, a little bit of oak hickory left. We've got pine, but it's not that deep green. It's sort of intermixed with more oak mesic hardwoods, lots of agriculture. So there's been a tremendous amount of land use change that's influenced our forest types, but we have really changed what's on the landscape because we suppressed fire and excluded it from these systems for decades. And now what the fire regime looks like is that far right figure. And you can see that mostly we're in shades of kind of a green or blue, which means we have very infrequent low severity fires. And these are mostly fires that we're intentionally returning to the landscape for restoration purposes, and rare fires, meaning only happening every 100 years or so. So we have dramatically changed both the fire regime and the composition of our forest due to fire suppression policies that were enacted in the early 1900s. And that, in some places, there's still a mentality of putting out fire if it happens. And it's unfortunately putting fire back into systems today when we removed fire for 100 years almost is not the same. Things have changed a lot. And that's the mesophication idea. And that now we've allowed all these species that don't really like fire to come into the system. And once they're there, it's not like you just throw a fire in and they're gone. These species actually have traits that reinforce a fire regime that they like. So they make it moister, more shady. They have leaf litter that decomposes very quickly so the fuel loads don't accumulate. They have leaf litter that holds a lot of moisture. So it's much harder to burn. So again, our forests are denser, they're more close canopy. And so the bar graphs at the top are showing sort of the acreage, the historical distribution of grasslands, open forest, and closed forest. And you can see we had a lot of grasslands, a lot of open forest, some closed forest, but not as a dominant forest type. Current day, land use, and this is mostly agriculture, has taken most of the grassland and open forests. And so most of them have been converted for agricultural ranch lands. And then most of the forests that we see today on the landscape are closed forest types, which you can see in that bar on the right. So the bars going down for grasslands and open forest means that was a loss in acreage. And then you can see the frequency distribution of open versus closed forest types in both the historical landscape and the current landscape in that bottom figure. And the number of trees per acre in open forest was much higher in the historical landscape than it is today in the current landscape, where we have mostly closed forest. So again, that shift in forest structure and composition from open forest that had a high abundance of fire-tolerant oak and pine species today to closed forests that have increased dominance by fire-sensitive tree species and a much higher tree density is driven by fire. So closed forests today usually have no surface fires, while these open forests had very frequent low intensity surface fires that were being driven by that herbaceous fuel in the understory. And so these are, again, thinking about that positive feedback of mesophication, meaning that you take fire out of the system, you get an increase in these fire-sensitive species. Those fire-sensitive species create non-flammable conditions in the understory, which then make the forest more conducive for their growth than the growth of more fire-tolerant species. So that's the positive feedback. It just increasingly gets worse over time for returning fire to the ecosystems. And we can see evidence across the landscape of this shift. So the panels at the top here are looking at pine ecosystems, and the ones on the bottom are looking at oak or upland hardwood ecosystems. And moving from left to right, from stands that have had fire restored and have been pretty successful at opening up the stand, creating more open canopied highlight conditions, getting more herbaceous species growing in the understory, to those on the right that have not seen fire for many, many years. You have much shadier conditions, changes in the fuel bed from being dominated by herbaceous species to being more leaf litter dominated. So the top right would be pine litter and the bottom right would be hardwood litter, most likely litter of species like red maple or sweetgum, sugar maple, American beech, those types of species. And so I'm really interested in thinking about this from the perspective of the tree. Excuse me. So if you think about a tree, they have a zone of influence, and their zone of influence is both like immediately around their bole, which is the darker red spot here, and then beneath their canopy, which is the pink spot. And if any of you have ever been into like a longleaf pine system that had a few water oaks or live oaks that are still left in that stand, you probably have seen this. And I have definitely seen this in upland hardwood stands where beneath the red maple, it looks quite different than it does beneath the chestnut oak. The litter is different. What's growing there is different. It's obviously more shaded beneath the crown of some species than other ones. The amount of leaf litter is higher beneath the crown of a tree than it is in the open space. And then because you have changes in leaf litter inputs and you have changes in the amount of light that's reaching the ground beneath the tree, that influences moisture availability of fuels and the fuel loading. So how much fuel you see in the understory of a tree is different than it is in an open space. So obviously that could vary with tree size. As a tree gets bigger, it's going to have more of an influence on the ground beneath it. So its zone of influence increases. But these zones of influences also change with the type of tree species that you have. And so different species have different crown volume. You know, more mesophytic species tend to have more leaf area. They have a denser crown that creates more shade. While like a longleaf pine, if you look up into its canopy, it's pretty open. It allows a lot of light to pass through that canopy. The amount of leaf litter that is input by different trees varies. So you might have a higher area of leaf in a red maple or a sweetgum, but by volume or mass, that input might be different. And then the morphology is quite different. I mean, if you look at a pine needle compared to a southern red oak leaf, compared to a sweetgum leaf or a red maple leaf or a beech leaf, they're not the same. They have different thicknesses, they have different waxy coatings. All of those things influence leaf litter outputs. So how quickly that leaf litter decomposes. It influences how flammable that leaf is, how that leaf lays on the forest floor. Does it curl up and provide a spot where a fire can catch it and carry it? Or does it pack down and become more dense and more moist? All of those things vary by species and they're extremely important. And then trees, both their canopy and their bark, influence the amount of rainwater that gets distributed to the forest floor beneath them. So if a more open canopy is going to let more rain in versus a more dense canopy. I think, you know, most of us, if you're walking around in the forest and it starts to rain, we all kind of intuitively know which tree species we should stand over to avoid getting soaked, and that's a canopy difference. And then stem flow is just the amount of rain that gets funneled down the bark or the bole of the tree down into a narrow zone around the tree. And that's kind of why I have those smaller zones around the bole of the tree, because stem flow, it's amazing how much water a tree will funnel in a rainfall event. We did studies where we would have 80 liter or about 30-gallon trash cans full of water after about an inch of rain around a red maple. And all of that water is coming down the tree, it's getting soaked into the ground, it's altering the fuel moisture around the zone of that tree. So all of these species level properties of a tree are a very important component of the forest that influences fire behavior. And if you start to think about this as the cumulative effect of trees of different sizes and different species, their zones of influences, coupled with the interspaces between trees or the tree-freeing zones, all of that coming together cumulatively is what determines fire behavior as bottom-up controls. So I've got two pictures here, one of a pine stand and one of a hardwood stand that has a lot of mesophytic or species that don't like fire encroaching into the understory. And you can sort of think, okay, well, here's a pine stand. We look at all these trees, you know, most of them have their zone of influence. And then we've got one mesophyte bole. And then if we look at this hardwood stand, lots and lots of zones of influences that are cumulatively affecting what happens in that stand. So looking down at this from the top, it would look something like this. And as you can see, as you get more and more and more and more species packed in there, their zones start to overlap and they start to create conditions in the understory that are really, really important for driving fire. So, one of the questions that we've had since I've come to Auburn, especially because in the Southeast, Sweetgum is this, I'm sure you guys all know this, but man, Sweetgum can grow anywhere, right? And if you try to burn Sweetgum, you can burn in the understory beneath it, but all you're really doing is knocking it back. It's really hard to get rid of it. So one of the questions that we had is, how well will stands burn as species like Sweetgum continue to proliferate, even in pine stands, which have a pretty flammable litter? And so I've been working with Dr. John Willis, who's a research forester at the Southern Research Station, and Arthur Mora, who's a PhD student with me here. And I think it's funny how neither one of these guys had pictures where they were actually looking at the camera. So they're both like looking down on the forest floor. But anyway, so they're both involved in this project. And what we are trying to do is sort of figure out if there's a threshold where if you have enough Sweetgum in your forest relative to the amount of pine litter in the forest, that your ability to burn it becomes less or it becomes harder. And so what we did is we set up an experiment where we had 6 fuel bed treatments. So we were looking at 100% longleaf pine, 100% southern red oak, and southern red oak is a fire dependent upland hardwood species, and then 100% Sweetgum. And Sweetgum is not a fire dependent species. And then we had different combinations where we altered the amount of pine relative to the amount of Sweetgum and held the oak litter contribution constant. So basically what we did is we went out and we collected litter of these 3 different species. So we would go out, like that's a patch of predominantly Sweetgum. And I had a bunch of students and we went out and basically hand-picked up litter of these different species. Longleaf we purchased, but Sweetgum and southern red oak collected. We weighed and sorted that litter by species, and we ended up picking up something like 320 pounds of litter for this experiment. And then we went out into the forest and we cleared plots of a known size. So we used a leaf blower to take off the litter that was naturally there. These plots were 2 meters by 2 meters, or about 6 feet by 6 feet. And then we placed our different litter treatments on those plots. So this is a treatment that had about 60% pine, 10% Sweetgum. And then we set these plots on fire. And we, acknowledging fully that burning a 2 meter by 2 meter plot does not represent landscape level fire behavior, but it did allow us an opportunity to distinguish differences in these different fuel types. And so we burned these plots and we measured a variety of different metrics that indicate fire behavior, like rate of spread and flame length, duration of flaming, all of that kind of stuff. And it was pretty interesting, actually, what we found. And we did this at 2 different sites, 2 different days that had different weather, only about a week apart. But we worked in North Mississippi at one of our field sites is called Spirit Hill Farm. So it's up by Holly Springs, not too far from Memphis. And then at Talladega National Forest, just outside of Heflin. And we burned in March. So one burn happened on March 6th, the other one happened on March 13th. All of these litters that we put out as to create these fuel beds, we put them out in January because that's when leaf litter falls, right? We wanted them to sit on these plots for about 3 months before we burn them to represent what litter would normally do. Because a lot of the burning in these forests is being done in the late dormant season. And so, a lot of the lab trials with burning, they take litter, the litter is dry, the litter hasn't had any chance to decompose. So it's very different when you have fire, or could be different if you have litter that's been sitting on the ground, getting rained on, whatever else, for a few months before you burn it. So our burn days were quite different. Our burn at Spirit Hill Farm, it was much cooler. The relative humidity was lower, the wind speed was slightly higher, and we only had 4 days prior to burning without rain. Talladega was much hotter, much higher relative humidity, wind speed was a little bit less. We had 11 days without burning, so it was very, very dry. And I'm pointing this out because obviously weather is important for drying, or for determining fire behavior, but these biotic feedbacks that are being driven by different species and their impacts on fuels or understory conditions could be really important, although they might not be strong enough to overcome something like weather. So I just want to point out that the weather was quite different on these 2 days. And what we saw in both of these burns was pretty similar. So I'm just going to show you some videos real quick, and then I'm going to show you actual data. So this is field burning with a field bed that has about 30% pine in it. And I'm not going to let it run the whole time. I just want you to kind of get the idea of how the fire is moving. But basically we just, laid down a line. So we had a ladder kind of looking up at the plots to see what would happen. And we had that fencing, the chicken wire around it, because we didn't want the litter to blow out or our outside litter to blow in. But if you have 30% of pine in the fuel bed, the fire moves pretty well. You get pretty rapid movement across the plot, and it does what you want it to do. So that's 30% pine, moving pretty quickly. And after that burn, pretty much all the litter in that plot was consumed. Now we're looking at pure southern red oak. So this is southern red oak. And I just want to point out that oak litter, these upland hardwoods, their litter is pretty flammable. Southern red oak will burn, and it moves pretty quickly. The flame heights are not as high as when you have pine, but the fire is moving pretty rapidly, and that plot got burned in about 2 or 3 minutes. Whoops, let's see. Okay, now Sweetgum. Here's a plot that was all Sweetgum litter. There's some pine needles that have fallen in from the trees above, but what we put on this plot was Sweetgum. So we laid down the line, and there are flames where there's torch fuel. Basically, what's going to happen here is once that torch fuel is consumed, this fire goes out. And this was pretty consistent across our plots. Sweetgum litter does not carry a fire. And if you look at what our Sweetgum plots look like, here's a plot after we burned it, and you can see kind of in the bottom or the right-hand side here, which area of that plot actually the fire consumed litter, and it's that little red bracket that I'm showing you. So if you had all Sweetgum litter, the fire just doesn't move. So I should also point out another aspect of this study that we don't have data on yet is we planted seedlings in these plots that encompass sort of a gradient from being very fire tolerant to not being fire tolerant. So we had shortleaf pine, white oak, red maple, and Sweetgum. So we're going to evaluate how these different burns that burn at different severities influence the growth and survival of seedlings. And then we also had these plots distributed across a gradient of canopy openness. So to look at the interacting effects of fuel type with canopy structure. So this is all kind of new data. It's pretty interesting. Here's the rate of spread data for both the Talladega and Spirit Hill Farm. And you can see at the bottom, we've got the different treatments going from 100% pine to 60% pine, 10% Sweetgum, down to 30% pine, 40% Sweetgum. So pine's decreasing, Sweetgum's increasing. And you can see rate of spread really drops off as you move from 60% pine down to 30% pine, but then another substantial decrease between 30 and 10% pine. And then with Sweetgum, the fire is not moving much at all. 100% southern red oak looks about 30% pine. But again, same trends at both sites. If you look at something like residual mass fraction, which is basically the amount of fuel that's left on these plots after burning, it increases with increasing Sweetgum. So Sweetgum presence in those fuel beds is dampening the amount of fuel that's being consumed. Now, the one cool thing about this is we were able to collaborate with actually a professor here at Auburn who's in aerospace engineering, of all things, who has a burn lab similar to what Joe was describing. And we recreated these burns in a lab. So here's the longleaf pine burning in the lab. So these are controlled conditions. This is completely air dried litter, pretty high flame height, and the consumption will be quite high. If you look at Sweetgum, much lower flame lengths, and then this fire is going to take a lot longer to go to the end, and the consumption values will be lower. So what's kind of cool here is that we can compare our field burn results to what's happening in the lab, and these are the lab data. So I'll kind of walk you through this, but on the left, you can see how the mass of litter in kilograms decreases over time. And the interesting thing here is that the blue, the red, and the purple are fuel beds that contain 100% to 30% pine. So they're decreasing the fastest. The yellow line are the fuel beds that contain 10% of pine. So there's a pretty big jump in mass consumption consumed between 30 and 10% pine. And then one thing that I find interesting here is that the oak and the Sweetgum don't vary as much in the lab burns as they do in the field burns. And so I think this is because that decomposition component that I was talking about before, where if you're using litter that has never had a time to decompose, then it could look, oak and Sweetgum could look quite similar. But Sweetgum, really thin, the leaves break down super fast. If they've been that litter's been sitting out in the field for 3 months, it's really going to change that fuel bed in a way that you're not going to see in a lab burn. And those differences, when you look at the tracked flame front, so this is just how fast the fire is moving. Those 3 treatments between 100% and 30% pine move very quickly. And then the 10% pine, oak, and Sweetgums are moving kind of similarly and much slower. You can see the oak and the Sweetgum also burned longer. It took much longer to consume that fuel. Another thing that we've been working on is, asking a question that if we go out and thin the mid-story mesophytes that are growing in the understory of a lot of these stands that haven't seen fire in a while, how is that going to influence the understory, and how could that potentially impact fire behavior? So I have a master's student, Stephen Cabrera, who is looking at these thinning treatments and mixed stands dominated by short-leaf pine and a variety of hardwoods here in Auburn. He's measuring changes in understory microclimate, rainfall distribution, how that thinning changes fuel composition and loads. And then we're planning on doing some small burns in these stands at different seasons to see the impacts. Okay, so to summarize real quickly, our current day forests exhibit legacy effects of fire exclusion on their structure and compositions, very clear across the eastern US. Unmanaged forests are more closed canopy with fewer fire tolerant species. And these encroaching species have different canopy and field traits that exert bottom-up controls on fire behavior. And it's interesting to me, and maybe it doesn't matter, but if you look at some of the most common fuel models that are used in this region, they don't account for species level differences in litter flammability, although they clearly exist. And so it's interesting to me that there's a litter model, but that model doesn't account for whether or not it's Sweetgum litter or pine litter, which could be really important. Okay, so that's all for me. I'm happy to take any questions that anyone might have.
Thank you, Heather.
You're welcome.
Nathan, do you have any questions in the chat?
I don't have any that have showed up yet, but we'll see if some come in here in a minute.
All right. Well, thank you so much. What we're going to do, guys, we'll go ahead and go to a break until 10:10. So you guys, everybody can.
Hey, Ryan, we got a quick question that just came in. Somebody's asking whether or not they think there might be a trick for reintroducing fire into these stands once mesophication has started.
Well, I think that's what we're hoping to get at with that last study that I mentioned, where we're doing that mid-story mesophyte thinning. And I should also mention that Stephen has an observational study. I mean, again, we're working with John Willis, the Forest Service, but one of the things that I think we need to do first is sort of characterize what fuels look like across a gradient of stand composition and structure to understand what the variability is that exists across the landscape, and then ask a question about thresholds for burning. So is there some threshold where you have a particular fuel type where it's much less flammable? And so that study where we had the different pine and sweetgum variations, there's really a drop off between 30% pine and 10% pine. So if you were to walk into a stand that had, you know, a fuel bed with only 10% pine in it, you might realize then that you've got to thin that stand. You've got to open it up. You've got to change the amount of light energy that's getting to the ground to dry out the fuels. And you've got to get rid of the mesophytic fuels from the stand and then put fire back into it later. So that's kind of what we're hoping to get at is some way to predict based on some simple measurements of basal area, which most of us are doing, what the fuel loads look like so that we can determine whether or not we need to do something else before just lighting a match.
Thank you. And Dr. Callie has asked, what about other fuels? Have you looked at 10-hour fuels or other things besides your fine fuels?
We have not, but that was a question actually that came up yesterday in a conversation that I was having, because we're thinking about doing some of this stuff in montane longleaf, and you know, basically starting out with some characterizations across different levels of restoration, and then thinking about, well, there may be variations in, you know, your coarser fuels across these levels of different restoration that could be important as well. I haven't noticed that much in the hardwood stands and these mixed stands we were looking at, but I think Stephen, at least with his study, he's quantifying all of that. So I think we'll have some idea about the importance of those fuels once he's done with that study.
We've got another couple questions that kind of run along the same theme. Is there a minimum stocking that you'd prescribe for pine in these fires? And also, you know, what timing of burns as far as time of year might help to promote fire in these mesophicated stands? Right.
So I don't have a stocking answer yet. Again, I think that some of the work that Stephen's doing, and also the students that's going to work in these montane stands with a colleague of mine at Kennesaw State, I think that those kinds of questions where we're just characterizing what the basal area is versus what the fuels look like, the load and the composition, we'll be able to develop some models that will help us determine, combined with these experimental studies where we're burning different litter combinations. I think that'll help us determine what the stocking is. I mean, honestly, if your stands are so well stocked that there's very little light getting to the ground, and you have mostly, you know, if you don't have a whole lot of light getting to the ground, it makes it a lot more complicated. And then timing, you know, most of what I've been thinking about have been dormant season burns, but that's a good question, right? Like, when in the dormant season do you burn? I mean, it would be quite different, I think, if you burn in the early dormant season versus the late dormant season, because that's the time, the early dormant season, when you're having pretty large pulses of fuel being dropped onto the fuel bed. And these stands that have leaf litter fuels, they're being the dominant fuel type rather than herbaceous fuels. And so I think if you wanted higher fuel loads and a hotter fire burning in the early dormant season could work, especially if the leaves are already off the tree, compared to burning later in the dormant season. But I think, again, it probably depends on your management objectives.